Hello guys, this is codeNcode and this is the fifth lecture of this number theory series. In this lecture we are going to study about prime factorization of given number n. But this time we would use sieve so that prime factorization of a number can be calculated in logN time. So what we are going to do, in this example I have taken an array of size 15. It may look like a 2D array, but it's actually a one-dimensional array. I just cannot represent all 50 elements in a line, so I have to represent them like this. So all the numbers that you see in a cell are actually their indices, and at each point I have saved -1. So we have taken an array of size 15 and initialize each and every element of this array to be -1. Now as you already know, we are going to work with sieve, so we start from index 2. If the ith cell is having -1 there, then it means it's a prime. So we start from 2 and we see, okay, at cell 2 we are at index 2 we have saved -1, so it have to be a prime. So what we would do, starting from 2 itself, we would go to all multiple of 2 and see whether there is saved -1 or not. If there is saved -1, then we would replace that element with 2. So these are all the multiples of 2, and since all the multiples of 2 were having -1 initially, so we replace them by 2. So what is this notation? I've just the upper one is the index, and by after the integer after slash is actually the value stored. Initially I didn't show, at this point I'm not showing -1 saved because the color itself tells that there is -1 saved, and it is important to show the index number of each cell. That is why I have to show both of them. So upper thing is actually index, and the lower thing is actually what we have stored at that index. So what it indicates is that the minimum prime divisor of number 28 is actually 2. The minimum prime divisor of 34 is actually 2, and so on. Now our pointer increments. Now we are at 3. Since at 3 we are also having -1, so 3 must be a prime number as well. So starting from 3, we would go to all its multiple, and if there is -1, we would replace that by 3. So we would go to 3 and replace it by 3 because there is -1. We would go to 6 and we would not do anything because here it is not -1 but 2. So we would not change it. We would go to 9 and would replace -1 with 3, and so on. So starting from 3, we went to all multiples of 3 and then replaced -1 by 3. So if you see, for 33, the 33 can be written as 11 into 3. So the minimum prime divisor of 33 is actually 3. That is why we are having 3 here at index 33. Now move on. 4 is not having -1, so it cannot be a prime. 5 is having -1, so it is a prime. Starting from 5, we would go to all multiple of 5 and see if there is -1, we would replace that by 5. So 5, 25 and 35 and so on, we went there and simply replace them with 5. Replace -1 with 5. Now we would move on to 6, and since it's not having -1, so it's not prime. We would move on to 7, since 7 is a prime number. So for all multiple of 7 which are having -1 at their indices, we will replace them by 7. So 7 and 49 are the only two numbers. Then we would move on to 8, 9, 10 and then 11, and then 11 is a prime number, so we would replace it by 11 by 11, and then we would go to 22, but 22 would already be colored by 2. We go to 33, it is already colored. 44 already colored, and so on. So I'm not completing it, but this time, if you remember the previous implementation of C, what we did, we went only till square root of n, but this time you have to go till n. The reason is because if you leave till square root of n, then these cells would contain -1, so you would not be able to print the prime factorization of that, because the method that we are going to use to print the prime factorization of a number is this. Say you wanted to print prime factorization of 38. In that case, you would run a loop while n is greater than 1. Simply print the element at n. So for 38, while 38 is greater than 1, while n is 38. So while n is greater than 1, print the element at 38. At 38 we have 2, so we would print 2 and replace n by n with n by 2, because at index 38 we are having 2. So 38 would be replaced by 19, I guess. Yep. So we would move on to 19. Here it is. So if you would not replace 19 with 19 by 1, 19 by 19, or basically if at 19 index we are having -1, so if you would not run a loop till n, then it would contain -1, so we would not be able to print the prime factorization of 19. So it is important to run a loop from 2 to n. So if we run from 2 to n, then at index 19 we would have 19. So from 38 we reach to 19, and at index 19 we would be having 19, so we would print 19 and replace n by 19. So n by 19 would become 1. As soon as you reach 1, you would get out of the you would come out of the while loop. So the prime factorization of 13 would look like 2 into 19. Now take another example, for example 48. At index 48 we are having 2, so we would print 2, and 48 would be replaced by 48 divided by 2, that is 24. So we would go to 24 and we again print 2 and replace 24 by 12. So we would move on to 12. At 12 we are having 2, so we would again print 2 and would replace it with 6, because 12 by 2 is 6. We would go to 6 and print 2 again, and then replace 6 by 3, and we would go to 3 and print 3, and then 3 by 3 would become 1, and as soon as n becomes 1, we would come out of the loop. So you see, this is how you print prime factorization. So what we would do, we would be using sieve. We would run a loop from 2 to n, and for each number when you find -1 there, you know that this is actually a prime number, so you'd go to all multiple of that prime number and then replace -1 with that prime numbers. So for each index, what we are actually saving is the smallest prime divisor of that number. So for 38 its smaller prime divisor is 2, for 50 it's 2, for 49 it's 7, and so on. To print the prime factorization of a number, all you have to do, while n is greater than n, print, if I call it ar of n, and replace n with n by ar of n. So this is the implementation of it. So we are taking an array AR of size 10 to the power 6. We define max n to be 10 to the power 6, and we initialize all the elements from 1 to max n to -1. We'll start from 2, we'll go till max n. If the ith element is having -1, which means it is a prime number. So starting from there, we would go till max n. For each prime divisor, for each multiple of I, we would see whether that multiple is having -1 or not. If it is having -1, then we would replace it with I. So this is how sieve, using sieve, we can calculate. We would first pre-process all the numbers, and then we can print the prime divisors or prime factorization of each number in logN time. So just play with this thing and try to and yeah, there are a lot of optimization you can do with this thing, and I am leaving that for you to do as an exercise. The more you play with it with this, the more you'd learn. So just try to optimize this code. You can actually, because there are a lot of optimization which I have left. So I hope you have understood this. If not, just leave a comment in the comment section. Until then, till the next video, keep coding. Thank you.